Hi and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about some basic parameters of the traveling wave and maybe a little introduction to waves in general. So let's start off with a brief introduction to what waves are in general. Well, you could think of a wave as being in some sense like a series of coupled harmonic oscillators. If it's a, let's call it a simple wave, then it's a series of simple harmonic oscillators. If it is a damped wave, then maybe it's a series of damped harmonic oscillators. And, there's more to it than what I've said. For example, you can have more than one set of waves interacting with each other, and that can create some additional patterns. But in some sense, you could think of a wave, for our purposes, as carrying a set of instructions for essentially what the medium that's going to carry the wave should be doing at each point along the medium at each point in time that the wave is propagating. Okay, so for example, let's say that I happen to have a string, and so that's going to be what carries my wave. So here's my string, and then you pluck the string and you get a wave that's being somehow carried on that string, like so. Okay, and so this might be like before wave. So this would be at equilibrium. And then this maybe is during wave at some time. Let's say t equals 0. And then a little while later, the wave may now look like this. Okay, so this could be during wave t equals, we'll just say sometime later. So it's sometime larger than 0. Okay. Well, first of all, what do I mean by this is like a series of simple harmonic oscillators? You could envision each little segment of this string as if it is moving up and down like the motion of a mass on the end of a spring. And each of these identical pieces is sort of an identical amount of mass kind of connected to a spring of identical basic properties like spring constant and equilibrium length and that kind of thing. But each spring has a different amount of stretch or compression at the same time. So, for example, like if you were to say this right here represents my fixed ends of my springs, then this spring is like this, and this spring is more like this, and this spring right here is really compressed like this. And so you have kind of a different parameter for each piece of the mass. So how do we describe this motion? Well, essentially you would expect the equation to look very similar to an equation for an oscillator. In fact, you'd expect it to look like the equation of a single spring at any given point, but with maybe different phase values. And so the phase values depend upon where along x you are. So if we were to take this axis right here as, let's say, the y-axis, and this axis right here as the x-axis. And note that the x-axis is also what the string should look like at equilibrium, then we expect this string or this wave to have some maximum displacement times some function basically of x and t, function of position and time. And it turns out that the simplest such function that matches a typical simple traveling wave, single frequency, would be given by y is equal to some maximum value times the sine of what we call the wave number, kW, times x minus or plus some angular frequency omega naught times time plus some offset phase parameter. Okay, so y max would represent amplitude or maximum displacement, and displacement. X basically represents position that we're monitoring, so maybe position of interest. T represents time. And then these other two, omega naught and phi naught, you're already familiar with. This would be angular frequency. So it is omega naught is given by 2 pi divided by the period t. And then phi naught is phase offset. So what about kW? What is this wave number? So kW represents wave number, and it's basically the equivalent of the angular frequency. So the wave number omega naught, kW, excuse me, is equal to 2 pi times not the characteristic time, the period, but rather the characteristic length, which we use a lambda for wavelength. So if I go back to my wave, so here's essentially my sketch of a sine wave. It's not very good because unfortunately I don't have the same distance from one peak to the next as I should. This distance right here and this distance right here would be y max and negative y max. The distance from one peak to the next, this would represent lambda. And so here also is lambda. You can also go from one trough to the next. That's also a lambda. And then time period is, if you allow these waves to elapse over and over and over again, how much time elapses if you allow this thing to play until you, let's say you're taking high-speed snapshots, you get the same high-speed snapshot a second time. So I take a picture, I take another picture a little while later, and maybe the wave now looks like this. Same lambda value, same y max value, but stuff has kind of shifted over, like I'm no longer at the minimum as I was in this picture. And then a little while later, maybe I happen to locally be at a maximum. Sorry for the crude drawing. Okay, and so on. Eventually, I will take a snapshot in time that duplicates this one right here. So again, I get to start off at 0 displacement and have my wave like this. So when that amount of time has elapsed to where I get back to this, that is one period. Okay, it has kind of the same definition as what a period had with simple harmonic oscillators. How long until the mass at the end of the spring, for example, returns to its initial position and condition. So if it was initially stretched out as much as you were going to stretch it, when do you get back to maximum stretch, and so on. Okay, so those are the basic parameters of this wave. One other note, and then maybe I'll do like a quick example. One other note, for mechanical waves, there are, and waves in general, there's kind of two types. So two basic types of wave. The first one is what's called a transverse wave, and that's what I've actually been drawing for you. So all the waves that I've drawn so far are transverse. Basically means the wave propagation is perpendicular to the displacement of the individual particles. The second type is what's called longitudinal. And longitudinal, I haven't drawn any for you. An example would be a sound wave, or if you took a slinky or a spring, and instead of moving your hand up and down like this so that waves travel this way, but so that the spring is also doing this, if you were to play it like an accordion, the waves would be traveling this way, but all the individual links would also be displaced to the left or to the right. And so displacement and propagation direction are parallel. So let's return to our equation again, and again make sure we understand what each of these parameters means. So y would represent at any position along the string how far has that element moved, either above or below, or to the left or to the right if you're talking about like a slinky or a sound wave or what have you. So how much has that element displaced from its equilibrium? Y max is the maximum displacement. Okay, that's the amplitude. Kw is called wave number. It's 2 pi divided by wavelength, the distance between two peaks. X is basically saying where along this string are you looking. So what position along the string are you looking in? You can do this also in 2 or 3 dimensions, so it could be just generally where in space are you looking. Then omega is your angular frequency, t is your time. You're already familiar with those from the oscillation, so we could go back to this and call those the oscillatory parts. In some sense, what these are telling you is the spatial component, the temporal component are telling you the oscillatory part of the motion, and then the coupling part of this bit of wave. And then this, of course, is phase. And then the last little thing on here to note is this sign. This sign is positive if traveling left and negative if traveling right. That basically comes from graphing some version of this equation and then putting in different values of time, preferably values less than the time period, and watching as the entire sine wave just kind of moves to the left or to the right. Okay, so those are the basic parameters of simple wave, and that's all that I'm going to talk about in today's video. So thanks for watching.